In the previous lecture, we studied about EK diagram and I told you that in EK diagram, energy reference can be taken anywhere between conduction band and valence band. However, in most books, you will see the reference of energy level is usually taken 0 at the top of the valence band. Let's take a simple EK diagram and alongside it, we will draw a conventional energy band diagram. I hope you can correlate between the two different diagrams. The minima of energy level of the conduction band in the EK diagram is at the same level of minima of energy level of the conduction band in the conventional energy band diagram. The same goes for the maximum energy of the valence band of the two different diagrams. After studying this much, did any of you thought about where the energy momentum plot in either conduction band or valence band will end, or even if it will end at all or will just keep extending? This lecture will answer such intuitive questions but in a very general manner. It will not involve much mathematics or derivation. We know very well that electrons can have two types of movement. One is interband and the other is intraband movement. Interband movement occurs due to the thermal energy when an electron makes transition from lower energy levels to higher energy levels after absorbing sufficient energy. Such type of electron movement is called interband movement because different energy bands are involved in the movement. However, intraband movement occurs within the same band. Suppose, for example, when an external battery is connected to a semiconductor crystal, it gives randomly moving electrons a certain direction to flow. But the question is, if the semiconductor is not connected to an external battery, then in which manner electrons will move? This property of electrons moving in random directions is studied extensively by various scientists such as Schrödinger, Harris Bloch, etc. Bloch theorems applies to wave function of electrons inside the crystal and rest in the fact that the Coulomb potential is periodic inside the crystal. As a conclusion of Bloch theorem, it can be stated that the potential energy function in Schrödinger's equation should be periodic. EK diagram of a semiconductor is obtained by solving Schrödinger's equation. If we have one proton and one electron like hydrogen atom, then it is easy to solve Schrödinger equation. But in solids, where there are large number of atoms and electrons, it becomes very difficult to solve Schrödinger equation. The answer to our question is this statement itself, that potential energy is periodic in crystal. There are actually three types of EK diagram, namely periodic zone, extended zone, and reduced zone EK diagram. When we talk about EK diagram, we know that on y-axis energy is represented and on x-axis momentum is represented. But from mathematical point of view, k can also be said as wave vector. Setting the reference of the momentum here to be equal to 0 and marking various points on the x-axis, you see we have different values of k like 2 pi upon a, 4 pi upon a. Here a is a constant which is related to the periodicity of the crystal. The diagram we have shown is actually periodic zone EK diagram, but as you can see, to study EK diagram of a semiconductor, then it is sufficient to study the region between the two red dashed lines. This particular region is referred as first Brillouin region. And the EK plot in this particular section will come out like this. And generally we study this EK diagram only, which is called reduced zone EK diagram. And the third type of EK diagram is extended EK diagram. In the extended zone EK diagram, different bands are considered for making the plot, which makes the final diagram quite complex. The actual EK diagram of silicon or any other semiconductor is quite complex. It is just a brief explanation, as I wanted to teach in the simplest manner possible. However, detailed explanation and derivation need solving of Schrodinger's wave equation, which is probably above the standard of graduate level students and are usually taught in masters. That's all for now.